So let's continue our discussion, plane motion of a rigid body. And recall, plane motion of a rigid body we have, in general, a translation occurring of all the points and a rotation about a point. So let's say we have this link here, and this link is following, point A is following some path, and point B is following another path, not necessarily the same path. I want to make this more curvy so it's more obvious when we throw some velocities on here. So in effect, what we have is we'll have maybe some velocity of B, say it's in this direction. Some velocity in A, in general, will go in this direction as it follows this path. It should be tangent to the path, but don't want to overwrite everything. And this thing itself is rotating with an angular velocity. So this equals some velocity then, translation velocity. Notice these are both velocity in the A direction, in location A and B, and added to that a rotation with an angular velocity here. So typically we call this a point that we're rotating about. We'll call this the base point. And of course, when you have a rotation like that, you have a circular arc here, and we'll have essentially a vector here that is tangent to this arc, which represents the velocity of B with respect to A. So we have general plane motion, which is a composite of translation and a rotation here about A. So let's look at the details concerning solving a problem like this. So to begin with, let's look at a link in the XY plane. Label this A point and B point, and this is a fixed reference plane. So let's string up some position vectors here. So we have a position vector to A, we'll call this RA, and we have a position vector to B. So you always want to think like this when you're solving one of these problems. Because it's easy for you then to understand that in order to get, this is B, in order to get B, if you start at A, you have to, so if you're heading up A and you want to get to the point B, then you have to head down B with respect to A. So R of B with respect to A. And that means you'll head in, let's use a different color. You'll head in this direction then. Right to there. So this is R of B with respect to A. And that always will be along the axis of the link. And as we will see, that is really convenient for our analysis coming up. So let's now look at a small displacement of A and B. So let's say our link starts over here on the left and moves to the position we see on the right. Really small displacement. We can characterize this or draw this displacement. Say we move in this direction for A. We'll call this D, like a little differential movement of A, and we'll do the same sort of thing for B. And we'll call this position DRB. Okay, well, so what has happened here is we've taken this and we have translated it to point A and then rotated it onto B. So the link has essentially gone through a translation and a rotation. I'm going to change the size of this. It doesn't actually change the size, but I'm going to do that so you can see these vectors I'm going to draw. So link AB doesn't deform in length at all, but what you end up with is a couple new positions. So we actually do a translation, which is the exact same size as up here, and I'll adjust things just a little. So this is still DRA. So we've got the DRA and DRB. Well, that means that this, let's go with pink, this guy here, between these two, is a little differential R of B with respect to A. So you have to travel this to here and then down to here to get exactly where B is. So we can write that out as this relationship, which should be pretty intuitive at this point. Now we can take this and we can divide by a scalar, dt. So let's divide both sides by dt, which means each of these individually are divided by dt. So now you have drb with dt, which is essentially the velocity of B equals the velocity of A plus the velocity of B with respect to A. So let's play the small displacement game again. We know then that this angle d theta equals essentially dr B with respect to A. Or rather, this drb with respect to A is, it resembles the arc length, and the arc length is r times d theta. So then, since r is constant, if we again take the derivative or divide by dt, essentially we get r d theta dt, this is not a dot, equals dr b with respect to a dt. So this side is essentially r omega. In fact, let's make that r red here, because this r really represents this, or r of b with respect to a. As we showed up here when we take a position vector. So, continuing with this idea, r of b with respect to a times omega is the velocity of b with respect to a. So, let's just put this in a balloon as a side thought here. So we can replace the velocity of b with respect to a up above here with that value. So the velocity of b then is equal to the velocity of a plus r b with respect to a times omega. Or in vector form, we'll present this as omega cross r b with respect to a. And this profound relationship makes life really easy for us. And it's easy because we can quickly, usually, determine our b with respect to a from a fixed point by just shooting two position vectors to our link in question.